Thanks, everybody. As she said, I'm Krycho, and I've been doing software for about 15 years right now. There's my family. You might have seen them running around the conference area a little bit. Over the last 15 years doing software, I've had cause right from the very start to think about how we build software that works well. When you're building aircraft software or things that check what happens if an oil refinery explodes, specifically to the people working there, some notion of correctness is going to tend to be on your mind. But even for somewhat more pedestrian things, you order some food for a restaurant, you want to get the right food and you want to get charged the right amount. And then I spent about 5 years working at developer tools and web frameworks at LinkedIn and got to see at every layer of the stack there what happens when your software isn't robust or resilient. You have frustrated developers, you have frustrated product owners, you have users who can't use the website that they want to use. And so for 15 years now, I've been thinking about this kind of important question. How do we make good software? Kind of a large question, right? And we're not going to get through all of the answers that you might give to it in this talk, but I'm going to give it a shot. So to do that, we need to actually think about what good software means. One is along the axis I just described, right? There are two things we might say. One is along the axis I just described, the software itself. Does it work the way it's supposed to? But there's another question, which is the software good in the sense that it's the right tool for the job at all, rather than being just assumed as software is good? Is it actually something that people want, rather than just something that's forced on them? So in short, is the software good both in its internal characteristics and also as it sits as a thing in the world? And we're going to talk through three big themes as we look at those two ways of thinking about good software. One is just engineering. How do we make the software itself good? And we'll see a little about how that goes beyond purely the code that we write. Another is modernity and intellectual modernism, and specifically how software and computing are not just artifacts of modernity, but sometimes are instantiations of the project, the intellectual project of modernism, and how that can be a very bad thing. And therefore, finally, humility. If we know the limits of our craft, both its internal limits and its limits as a thing in the world, then we can be somewhat better equipped to make good choices about building good software. What we build, how we build it, and sometimes what we say, no, I'm not going to build that too. If we're going to talk seriously about this, we kind of need to know what software is. Peter Naur, 40 years ago, in a paper we'll come back to a few times today. If you haven't read it, you should read the whole thing. Programming is theory building. It is important to have an appropriate understanding of what programming is. If our understanding is inappropriate, we will misunderstand the difficulties that arise in the activity, and our attempts to overcome them will give rise to conflicts and frustrations. Some things haven't changed in 40 years. So what is software? Well, for the purposes of this talk, I argue that it is two things. It is artifact and it is system. Artifact is the answer we tend to reach for when we ask what software is. The code we write, the text we create, the bits that compiles to. And that is part of it. It is a necessary but insufficient condition for software. It's kind of like the score to a piece of music. Composer and conductor Emer Noon, best known for conducting video game music, you've probably seen her if you've watched any videos of that, said recently, the score is potential energy. It's the potential for music to happen, but it's not the music. Now, you can study a musical score on its own terms. You can understand the composer's intent, understand and analyze her decisions, write a thesis on the artifact even. But if you never actually listen to the piece of music being played, you're ultimately missing the point. The score is secondary. It exists in service of making music. And software is similar. The textual source for a program, even the compiled artifact, is actually just potential software until we run it. It's an inert artifact, and it's important. You don't get the software without it. And you can do things like read code to learn from it, to study its design, analyze the way that software works. But if you don't run the program, you're missing the point. And once you run the program, it starts interacting with things beyond itself. It gets input from users, it has to deal with operating system interrupts, it might run out of memory, it might get hijacked by somebody who has studied the artifact and figured out how to use it to hijack the entire operating system it's running on. At one point in my time working at LinkedIn, we had this growing set of memory leaks in some Node.js servers, and we were unaware of those memory leaks. And eventually they got bad enough that every time we went long enough between deploys, like say over a long weekend, the whole site would go down for some large swath of our users, and you would not be able to use LinkedIn at all. And as we dug in, what we realized was there wasn't a cause of that set of bugs. Instead, there was this whole complex mix of factors. We had long-standing technical debt in the way those servers were implemented. We had gaps in observability. We had increased load on the system. The app was getting bigger and we had more users. We had system-wide configuration mistakes that no one caught in code review, which led to thundering herd shutdowns of all of our servers. We had an org-wide right-sizing initiative going on that was decreasing the total amount of memory available, even as we had leaks causing more memory usage. And we fundamentally had a lack of resilience. There was only one place in the entire system that could say, whoops, that node's unhealthy, restart it. There's a whole host of bad things, but critically, no one had a view of that as a system, as a whole. People knew a lot of things about the individual artifacts, but not about that whole picture. The authors of the original code had moved on. They'd left a presentation here and a document there, so maybe you could understand some parts of it, but the folks doing the right sizing, for example, had no idea that this system works differently than every other system at LinkedIn. And it represented like 1% of our servers or less. So this system was broken. And it was therefore the whole system which required us to understand it, to add observability to it, to get a theory in our minds of how it worked, and then to be able to try to fix it and see if our fixes actually worked. So software is both artifact and system. It's the code we write and the whole thing running out in the real world. And if we want to make software good, we have to tackle both parts of those. So what do we know about making good software artifacts? I'll start by pointing to Eric Evans' domain-driven design, which I think is one of our best tools for authoring code. The big idea, if you haven't run into this, is to explicitly use the language of whatever part of the world your software is working with. The types and functions in your code should use the same nouns and verbs as the people who actually do the work. So to borrow an example from the excellent DDD by example GitHub org, if you're doing software to support a library, then your code should talk in terms of books and copies and holds and checkouts and catalogs and patrons and librarians. You should have functions that let patrons place holds on books from the catalog and events for when a hold on a book becomes available and state representing the copy of a book in so on and so on. You get the idea. This is really powerful, and it's increasingly common across large swaths of the industry, especially the functional programming world, but also things kind of functional influenced and adjacent. Rust, Swift, Kotlin, you'll see a lot of this. And I think one of the major reasons it has caught on is because Ron Minsky gave a talk a decade ago called Make Illegal States Unrepresentable. And he showed in that talk how you can combine good type systems with domain-driven design to make for much more robust systems and how they model the world. The kind of classic example here is, let's model the state of a request. And we know that the request might still be loading, or it might have finished loading, in which case it'll have a value associated with it, or it might be an error, in which case It'll have some description associated with it. I have here a very classic version of how you might model that in your types, which is very easy to mess up. This is a Rust example, but I've seen almost exactly this code in JavaScript, Rust, Java, C#, you name it. The problem is you can end up with a data which has loading is true, loaded is false. Okay, that's fine. Error is true. Wait, it's loading and an error? But there's some value and there's no error description. Oh, no, this is bad, right? And Minsky's insight was, no, we can actually change how we represent this. We can make our representation map to the states that we want to exist in the world. So now it can be one of loading or loaded with the value or an error with a description. And so when we construct it, we can't get it wrong. The type system will no longer agreeably let the bad code go by. And this is great. A lot of bugs just disappear forever when you do this. So we can make our software good internally a lot more easily when we make its assumptions about the world explicit rather than implicit. When we make the program structure and text and types encode those assumptions. And it's a lot harder when they're implicit, as they were in the first case. The same business rules apply, but you couldn't check them. We can go further than that on what I think of as the output side. We can go so far as to use proofs and formal verification where it makes sense. If you're building a TLS implementation, reaching for F-star or lean or agda might make a lot of sense. It's a mathematically tractable problem that's incredibly important to get right. And that, if you've never poked at it, takes the kinds of things we just saw and dials it up to not 11, but like 17. And it's very effective, and it's very expensive, and there are diminishing returns. But TLS is important, so you can get a lot of things out of that. On the other end of the spectrum, we can also apply formal systems analysis on the input side to our authoring. We can reach for tools like TLS or Alloy Plus to write specs that are, here's what the expected behavior of our system should be. And if we do that, we can then run those model checkers over it and say, did I miss any really important edge cases? And they will say, yes, you did. You need to fix this case. And then once we've done that, when we go to do the work of authoring the code, we can have something actually verifiably reliable to point at. And that's excellent. Last but not least, testing. The old standby, it's been around for a long time and for good reason. We can write regression tests. If there's a bug, we can write a test that reproduces it, then fix it, and then we know it won't come back. We can do test-driven design, which I love not least because it's one of the best ways I know of to find all the coupling points in your system, and therefore to make conscious choices about, do I want this point in my system to be coupled? We can do property-based testing to cover cases that we would not catch or think of as humans because the state space is so large. We can do performance testing and get some sense of the actual behavior of our system at runtime. Is it fast or slow? And this matters a lot for our users. And testing kind of takes us to the edge of systems. So what do we know about making software systems good? I think the answer is somewhat less. And a big part of that is because a program has some sequence to it. It might be a complicated one, it might be an asynchronous one, but a system does not. As Donella Meadows puts it in Thinking in Systems, systems happen all at once. They are connected not just in one direction, but in many directions simultaneously. And this can be hard to get our heads around. And one reason for that is that software construction is the construction of a static artifact. And some of our best tools for making those artifacts better, as we just talked about, are static tools. So it's easy for us then to want to try to make our systems better by making them static and therefore more amenable to static tools. But here's Meadows again. Resilience is not the same thing as being static or constant over time. Resilient systems can be very dynamic. Short-term oscillations, periodic outbreaks, or long cycles of succession, climax, and collapse may in fact be the normal condition, which resilience acts to restore. And conversely, systems that are constant over time can be unresilient. So building good software systems means thinking about how the system behaves dynamically in time and space, including what happens when it breaks, because we actually cannot build software systems that don't break. Even if you got the formal artifact perfect, hard drives crash, networks lose power, cosmic rays flip bits in RAM. No amount of domain-driven design and type system rigor is going to help you when the RAM goes bad. As a friend of mine likes to put it, at the end of the day, physics always wins. So, what do we do when our artifacts break? And the question is ultimately, how do they handle unexpected errors or just unexpected conditions? I think Erlang's model is a good starting point. Let it crash. Sometimes the most robust systems we can build are those which are full of artifacts which know how to just say, something weird is happening, I stop. Please restart me in a healthy state. That gets rid of bad state. Might get rid of your memory leaks or at least reset them to 0. It's very helpful. But unfortunately, you have to handle a crashy system well, because if you have a system full of things which just crash when things go badly, you can make things worse. Each component has to actually be resilient to the components around it crashing as well. Otherwise, you end up in the situation Canoe Lee describes. Your beautiful crash-only error handling strategy has nudged your system into a new equilibrium, where the backend is continually receiving too much load. A local defect has been amplified into a global system outage. Even if you remove the crashing defect, the flood of retrying startup queries may persist as a metastable failure mode of your system. I've seen that before. So our systems also need to build in things like exponential back off and back pressure and so on. And that might seem obvious to you, but I saw someone try to roll out a new piece of core infrastructure at LinkedIn a couple of years ago that didn't have that, and it went very badly. We also have to be able to understand the behavior of our system in all that dynamic glory over time. I alluded to this in that example from LinkedIn earlier. We need visibility into the system. If the system is increasingly unhealthy and no one knows about it, it can go from seeming fine to, oh no, the users can't get to the site, like that. And that's what happened to us at LinkedIn. Everything seemed fine, and then the site was down. And fixing it involved, as I suggested, a lot of experimentation. What happens if we make this change to this artifact? Does that help? What about that artifact? Can we do this other thing and the system still actually sustain its load? Oh, no. So we needed visibility. And tracing and monitoring are not sufficient to running a healthy system, but they're sure as heck necessary. You're just not going to be able to do it without them. Okay, so far so good. We have made some progress on static artifacts and how we make them a little better. We've gotten less better, but still better over time at making resilient software systems. But let's look at request data again. What state transitions are legal here? You can't tell. The code doesn't tell you. And I can talk to you about using type state to make it explicit in the code later. But even if we did that, why is there not a not started state here? Why is there not a retrying state here? In other words, why did we choose this representation and not some other representation? Now, presumably we have reasons, and we could document them, we could write them down. But I will tell you that even that can only go so far. Even when I worked on aircraft software, in the most waterfall design up front process I've ever seen anywhere, and for good reason, aircraft, we didn't comment everything. You can't. If I write a for loop, did I just do that because I prefer imperative programming to using .map on a collection? Or is it load-bearing? Is it a performance optimization that's really important right here, but only for this specific version of the compiler we're using? Well, maybe in that case I write down a comment. Do I write it down every single time I call .map or use a for loop instead? Of course not. It would be exhausting. We would just run out of time from just trying to explain all the things that we do. A lot of them necessarily live in our heads. And when we design and build software, we always have in our minds some model of the thing we're trying to do. And that model is always incomplete. It's fuzzy around the edges. And it's usually implicit. But even when we try to make it explicit, it's lossy. Here's Peter Naur again, back in 1985. The theory, what I called a mental model, built by the programmers has primacy over other such products as program texts, user documentation, and additional documentation such as specifications, in at least 3 essential areas. 1, the programmer can explain how the solution relates to the affairs of the world that it helps to handle. 2, the programmer can explain why each part of the program is what it is. In other words, is able to support the actual program text with a justification of some sort. And 3, the programmer is able to respond constructively to any demand for a modification of the program, so as to support the affairs of the world in a new manner. Naur's not joking when he talks about comments and design documents not helping. They're not new, after all. The very first page of the paper, he writes, in several major cases of a software project he had observed, it turned out that the solutions suggested by Group B, who were not the original authors, were found to make no use of the facilities that were not only inherent in the structure of the existing program, but were discussed at length in its documentation. Again, that rings true. Have you ever looked at a piece of code that you needed to change and carefully read all of the source and read all the associated documentation and opened a change request and had the authors of the code say, oh, thank you, that's well intended, but that's not how you do it. You do it this other way. That happens because the authors know the intended structure and working of the code. They have a theory of it. But even when they try to communicate it, that communication is incomplete. It's deeply lossy. This is actually one of the reasons that everyone hates working on legacy code. Legacy code is inevitably code somebody else wrote, and therefore code for which I don't have a theory. I don't have a mental model. That model and theory always lives in our minds. So an architecture.md file is useful, but it's not the model. Comments in the code are useful, but not the model. A 5-hour YouTube series explaining all the internals of a tool you built is maybe useful, but it's not the model. Ask me how I know. The code itself, in fact, is not the model. It is our best attempt to implement the model, but it's not the model. The model is in our minds. And it turns out this is directly related to what makes building good software hard. When you're building software, you make an incredible number of decisions. Am I going to capture this business rule using an enum or a struct? Am I going to use an optional here, or am I going to reject that missing data at the boundary, at the API call? Am I going to reach for an interface or a concrete type here? And if you had a junior sitting next to you, you could explain, most likely, here's why I did that this time. Here's why it's appropriate. But could you write a program to decide those things? You could not. You're a programmer. If you could, you'd have done it already. You can't actually encode those decisions. And the reason is that the knowledge is, first of all, tacit. It's embedded in our experience. And second, even when we try to make it explicit, it's contextual. It's difficult to generalize. Even the heuristics that we tend to share most confidently, like don't repeat yourself, get their own counter-aphorisms, like Sandy Metz's prefer duplication to the wrong abstraction. And even if you came up with some set of rules and baked them into some decision tree that somebody could follow mechanically, we all know that wouldn't be good software. Peter Naur, again, if the exercise of intelligence depended on following rules, there would have to be rules about how to follow rules and about how to follow the rules about following rules, etc., in an infinite regress, which is absurd. Not pulling punches here. The decision space is basically infinite, so it requires judgment. In my experience, good judgment is actually one of the key markers of an actually senior engineer. Do we tackle this particular issue with a little process change or a little bit of code? Or neither, because we judge the problem is not that costly and the solutions would be more costly. Seniority in that sense is not just years on the job, but it's growth in a particular kind of knowledge, which is what James C. Scott describes in his book, Seeing Like a State, as a wide array of practical skills and acquired intelligence in responding to a constantly changing natural and human environment. Metis, from the Greek word for hand knowledge. This is an example in Scott's book of what people do. He doesn't mention programming basically at all. And his classic example is how traditional farming communities know things like, it's time to let that field go fallow. And then when we plant it again, which plants are we going to plant in that field? And then what order do we rotate the crops through? And then, oh, that crop is not doing well. I'm going to plant a different crop next to it, which is actually going to help. Sometimes this gets pejoratively or complimentarily described as folk wisdom, the kinds of things that local communities know and science hasn't caught up to, because there are an infinite number of biomes in the world and too long to study them all and so on. And it's including that, but it's not just that. It's also all the kinds of things that we all do that you can't learn without the doing. How do you stir the dough when you're making bread? How do you ride a bicycle? How do you, reach open and prop the grocery bag on one leg and manage to get the door open because you brought too many bags with you? That's metis, that whole range of kinds of things. And metis is the kind of thing that governments and businesses, bureaucracies in general, have had a bad tendency historically to stomp on in the pursuit of legibility. If some practice, some way of doing things in the world is legible to you, you understand and can, at least to some degree, articulate that practice. So most people's own work and culture is fairly legible to them. Again, you can explain to that junior, why did I do this thing? Now, a trick is that the act of programming is fundamentally and inescapably an attempt to systematize the world. It's an attempt to make the world legible to computing systems. That's why we use formal modeling and types and tests and domain-driven design and so on. And if we think back to our request data example from earlier, what we're actually doing here is trying to make our own design decisions legible to ourselves in the future. When we add tracing and observability, we're trying to make a system more legible to ourselves. And so far as it goes, that's a pure win, because our software is less buggy and more resilient. It's a better time for our users. But legibility can also name the ways that big bureaucracies and software can actually go very wrong by not just trying to understand or categorize, but ultimately trying to rationalize people's practices in the world. And that can range from standardizing how people's names work, which they might not particularly appreciate, to enforcing the scientific management of forests, from which some of the major European forests are a century and a half later still struggling to recover, to destroying local farming practices in the name of modernization. The Soviets and the capitalists tried this in the 20th century, and both of them caused millions of people to starve to death. There are two paths when we think about legibility. One is to embrace the fact that legibility of the world is limited. It's important, it's essential for pursuing a lot of good goals, but it's limited because it's always going to be local and contextual. The other is to try to reshape the world so that it can be legible to us at scale, to try to smooth things out so they are regular and predictable, so that they are measurable and controllable. And that second path is where danger lies. I want to be really clear. The desire to understand and improve the world is good. Wanting to raise people out of poverty is good. And that's what both the Soviets and the capitalists were trying to do with farming modernization. But this can go very wrong when it transmutes from a desire to understand the world and to improve things into a desire to master the world. And that's what happens when we take the joy and goodness of things like scientific understanding and tool making and building bigger things together than we could apart, like Saturn V rockets to go to the moon. Those are good things, but when we turn them into everything and we think all of life should have that shape, things go badly. The High Modernist project was and is just such a twisted version of good ends. Scott describes it as a strong version of the self-confidence about the mastery of nature, including human nature, and above all, the rational design of social order. Donella Meadows suggests people who are raised in the industrial world and who get enthused about systems thinking, hi, it's me, are likely to make a terrible mistake to assume that here, in systems analysis, in interconnection and complication, is the key to prediction and control, because the mindset of the industrial world assumes that there is a key to prediction and control. And if someone believes that the world is amenable to control, that it should be controlled, usually by them, it's easy to justify doing terrible things in the name of good ends, to rationalize the world by eliding all the inconvenient local details. The High Modernists also had power, so they could rationalize things without consulting the people affected. And that meant that they missed out on an awful lot of meatus. And therefore, they regularly ruined the lives of people they were legitimately, genuinely, earnestly trying to help. When you throw away generation upon generation of hand knowledge about how the land works, bare minimum, you're going to make a lot less money from those crops than you think you will. Maximally, again, you end up with starving people. Now, again, legibility is good. It's inherent in human life. It's inescapable. But, as Scott puts it, the necessarily simple abstractions of large bureaucratic institutions can never adequately represent the actual complexity of natural or social processes. The categories that they employ are too coarse, too static, and too stylized to do justice to the world that they purport to describe. That is a potentially damning description of software artifacts and systems. It's hard not to build software like that. For one thing, it's really easy to forget just how much we left out of even our own theory of the world in a particular set of design choices, right? When we build request data, this is our world. We're in charge of it, and this is lossy. You can think of it like lossy compression. Think about all that we left out. It's really easy to slip from this, where we are actually in charge, to the world of the library, where we're not. We're trying to serve librarians and patrons, and forget that the lossiness is worse because the world is just shockingly complex. John Salvatierre, a couple of years ago, wrote a blog post with this title, which is great. Reality has a surprising amount of detail. The edge cases end up infinite because the world is infinitely complex. And that makes it, to say the least, hard to model with software. And we need that reminder because we're constantly tempted to indulge in the high modernist move. It's a lot easier, especially from the position of ascendancy that software has as a field right now, the power that we have as a field right now, to force the world to fit our programs than to make our programs adaptable enough and flexible enough and fuzzy around the edges enough to fit the real world and the real complicated ways that people work and play and live. Concretely, it's easy to define connection as good, just unambiguously good, when to you connection means the nodes in a social graph database, than when you realize that my local arts community and modern slavery are both potent forms of connection. Connection is much too thin a concept to do justice to the difference between those two things. That's what most social media algorithm graphs do, though. Likewise, if you use an algorithm that favors engagement, which is another concept too coarse and stylized to do justice to the difference between hate reading and delight, you can end up with genocide. And I'm not being cavalier here when I use words like slavery or genocide. This kind of flattening and compression is a real part of how we get trafficking of minors on Instagram and a genocide in Myanmar in the last decade. And I'm not picking on Meta here. Those examples happen to come from Facebook and Instagram. I think they're a function of scale. And in particular, trying to achieve the kind of scale that Meta has with the specific kind of profitability that Meta has. You have to flatten things out. Metis doesn't scale. Legibility doesn't scale. Myanmar happened because local people knew what was wrong and they couldn't get the big system to understand. As software practitioners, our default answer to should we build this is, well, yeah, especially if there's a really cool technical challenge involved, right? Like scale. We have to remember that with very rare exceptions, we're not building things for ourselves. We're building things for people out in the world who have their own interests and their own concerns. And most of the world is not and should not be about computing at all. Computing should be about serving them. To put it another way, as a class of people, we software engineers really hate it when capital M management tries to turn us into interchangeable cogs. We hate it when people refuse to understand that building things actually does just take time. And we really, really, really hate it when someone insists on rushing feature after feature after feature out the door in sprint mode and also complains at us, the same person, that stuff is broken now and why are things taking longer to ship? We hate that. So what gives us the right to do it to other fields of human endeavor? We should turn it around. As software developers, craftspeople, we should sympathize very, very deeply with all the other craftspeople, all the other people whose work is meatus in the world. And the reality is that's most of them. And the standing desire of, again, capital M management, which let's be clear, is not all managers, but that desire to regularize software development, it's the same desire as the high modernists had to rationalize crops and soil and shops and neighborhoods, and generally mess them up in so doing. My friend, the architect Levi Wall, summarized, disruptive logic often requires an oversimplification of a perceived problem. We have to resist the temptation to make quote-unquote problems more tractable by flattening out the surprising amount of detail in reality. Which means that we need to be willing to push back against building software that we shouldn't be building, or in ways that we shouldn't be building it, because that's what's entailed when we take the title of engineer. A sense of responsibility for what we build, and yes, therefore, sometimes the refusal to build something if it's wicked or foolish or both. And that, yeah, will get you boxed out some places. It might lead you to quit a lucrative job rather than to keep building something which isn't actually good. But the only way we get to good software, which is what we're talking about here, right, is if people like us consistently, indeed insistently ask, is this software good? Because if it's not, I won't build it. We could end there. I think in some ways that would be a good place to end. But it would also be a little depressing. So I want to turn it around and leave you with a challenge instead. How do we look at that and say, okay, that's right, I think. So how do I build software that serves its users instead of subjecting them like the high modernists did? In particular, how do I leave enough affordances in my system for all the things I have not considered inevitably. This is, I think, the underrated power of tools like spreadsheets. They are open-ended enough that you can do all sorts of ridiculous, incredible, both kinds of things with them. You shove enough macros into an Excel file, treat it like a database, and suddenly you're running a very large, successful business on it. And as working programmers, we don't really like that. We get bothered. I get bothered by some of the systems that come out of that. They don't scale, we say. Yep. They're unmaintainable messes, we say. Also, yep. They're kludges all the way down, we say. Again, yes. But at the end of the day, the person using that spreadsheet could do things that the person who came up with spreadsheets in the first place, and for that matter, programmers working on Excel or Pages or even Airtable today, can't imagine, because of the endless complexity and variety of the world. And that's amazing and beautiful. We should be looking wherever we can, how do we make that kind of thing possible in our software? But this is, to say the least, not trivial. I think you all know that. Here's Peter Naur one last time. In including flexibility in a program, we build into the program certain operational facilities that are not immediately demanded, but which are likely to turn out to be useful. Thus, a flexible program is able to handle certain classes of changes of external circumstances without being modified. However, flexibility can, in general, only be achieved at a substantial cost, which bluntly is why we don't do it much. It's expensive, and it's hard. It's particularly expensive and hard when we're trying to build good software which is robust and resilient from the outset, which does actually respect the surprising amount of detail in reality, which reinforces metis in the world rather than undermining it or demolishing it, which ends up enabling and empowering and elevating the people who use the software rather than making them feel frustrated. This is hard. Building a tool that requires many ways of using it is just massively more difficult than building one that works in just the one way we imagined. But we're all here today because computers are that kind of tool. Software is that kind of tool, can be at least. Programming languages are like that. And the truth is that computers are a part of everybody's world now, whether they want that to be the truth or not. So we owe it to the people we are serving with our software to honor them in that. And I think this requires us to apply all of our rigor. We're not giving up on type-driven development and test-driven design and observability, and we need all of that because this is hard. It also requires perseverance because it's hard, and it's going to be the kind of thing that if we take this tack, we get it wrong and find out that's not flexible enough, that's not robust enough, and we have to take another swing at it, and another swing at it, and another swing at it. And finally, it requires imagination. How do we pull together all of those things that we know about resilience and robustness in software development and apply them to software that actually does respect and indeed flourish in and help people flourish in the endless strangeness and, frankly, the glorious illegibility of the world? It's hard, no question, but it's a challenge that I think is worth pursuing. Thank you. We do have 5 minutes here for discussion, so.
Who wants to go first? Okay.
Lots of competition here.
Okay, so very quickly, some people sometimes say that this meeting should have been an email. I think this presentation should have been a keynote. So that's one thing. The other, I just want to I wonder what's your view on. I don't know if you have this experience, but I have some colleagues who are in this field after like 15 years or 20 years, and they become cynical in some sense that when they were young, they were all about type safety, rigorous, all of that we strive to get. But now they tend to say things like, correctness doesn't matter, it only matters what stakeholders think matter. We make this change because there's some VC who needs this change because, right, whatever the reasons behind the business, and it's just hard to be that person you advertise in the world that it's designed the way it's being designed. And I don't know if you have this view, but that's what I tend to find when I talk to other folks, friends or colleagues.
I find the same. I think it is a natural place to end up. And as I was telling a friend recently, I'm in this constant war not to become cynical and to keep some hope that we can push further this way. I also think where we are is not inevitable. There's always a tension with getting a business that works well enough that you can actually keep building the thing you're trying to build. That's real. And I think one of the dangers, which I didn't talk in the talk about here, but I think really is pervasive for folks like us in this room, is the tendency to think about correctness for its own sake, rather than what is the kind of correctness and robustness that matters to the end user. And there's a way to talk to, and it doesn't always get through. I've been in the rooms where it doesn't. But there's a way to talk to that person that says, you're not wrong. What I care about is how we make it correct in a way that matters for our users, the people who actually get to or have to use this software. And one of the pieces of software that prompted this talk was the story that went around last year about people who are unable to actually pay for parking and end up with tickets because the only way you can do it is with a smartphone. And if you have a sufficiently old or sufficiently janky smartphone, you can't even get the app, and now you can't pay it, and you were trying to go to clear up something for your state of life, which is complicated and messy anyway, and now it's worse. And that's why I care about correctness. It's not for its own sake. It's for those people. And the message I'm trying to figure out how to convey is that message to the people who do get stuck on kind of stakeholder capitalism in an unhealthy way. But I don't think we know. I think I'm just going to keep giving this talk and trying to persuade people.
All right, thank you.
Yeah.
So, that was a lot.
Yes.
I had a comment and a question. One, a lot of what your talk went over reminded me of two quotes from Don Knuth, which is, the first one is, science is that which we understand well enough to teach to a computer, and art is everything else. And the second quote, which given how really, really precise and fastidious he was with language, I don't think is an accident, is the fact that he named his magnum opus the art of computer programming.
Yep.
I think that dovetails into your point really beautifully. Two, one of the things that I saw when I was still in the Bay Area and working at or around the cyberpunk megacorp-sized companies that are there is that if you get an engineer like that at one of the endless happy hours that always happens there, because that's the only way that these people, that's the only way that these companies understand how to socialize.
Yeah.
And you ask them, so what else is going on in your life? What else do you do? And they're like, okay, I'm not on camera. They give you a blank like deer in headlight stare, and they might say like, I play Quake, and that's it. And I feel like this is weird for me because when I was an intern and I was dealing with a bunch of people that started out on punch cards, and they gave me a lot of grounding on like where this medium was. They also, they were talking about building box plots for the garden because the soil they were in wasn't working right, and they were trying to debug that, and they were working on the CNC machine that they were designing. They were doing a bunch of other things that maybe were technical but weren't just staring at a screen endlessly. Right. And I feel like that's one of the reasons why a lot of the people in our computing generation don't have metis, is that they haven't been exposed to it at all in any part of their life.
Yep.
And it's really, really hard for me not to think that that's kind of by design.
Yeah, I think sometimes it's by design, but I also think a lot of times it's just easier.
Right.
And we like easy. But sometimes the hard thing of knowing how your garden works or how your food actually gets grown is good for you.
Right, yeah, exactly. I need to stop now. We can talk for hours on this. Thank you so much.
Yeah.
You had a question? Oh, okay.
Well, I mean, yes, but this sort of like plus ça change, plus c'est la même chose. The world is a messy place, always has been, probably always will be. That kind of thing you just talked about there, people getting their heads kicked in for completely ridiculous reasons, long predates programming.
It does. Yep.
So I mean, you're expressing you're expressing, in a sense, a utopian desire that is constant and is not at all bad. I'm not trying to shit on it.
I'm with you, actually.
You know, it's trying to make things better that we've been trying to do for a long, long time. And you know, in terms of software, I mean, you know, some software needs to be very specific.
Yep.
Some software needs to be general. I mean, the mention of Knut is interesting. So I was at a talk from Guy Steele, and he said, you know, any sufficient, and this gets to your point, any sufficiently complex data structure eventually is going to be like a minimal programming language.
Yep.
You got to build that in at the beginning, and the problem with tech was that Don didn't do that.
Yeah.
Yes.
Yeah. No, I think that's right. And I think, so the reason I connected software to high modernism is exactly that. We don't have to be high modernists when we build software, so we shouldn't. But like we're connected to these other intellectual lineages and projects in the world. And it's really important, I think, for us as software engineers to know, oh, these are things, as you just said, that are much larger than just software. And to think about ourselves as part of those projects for good or for ill, and to say, no, I don't actually want to be a part of that project. I want to be part of this other countervailing project that's ongoing instead. So that's the hope.
It doesn't have to be necessarily utopian, right? If you watch Cloud Atlas, the movie, it just might take centuries.
Yes. We're at time and past, but go ahead, Les.
It can be utopian because it just has to work. Like I want to talk to you.
Mm-hmm.
I also write a lot of aircraft software.
Yeah.
Like this is not like we all fly on planes that have to work, and all of this has to work. So this can't be utopian. Like we have to figure out how to do this.
How to do it.
To a reasonable degree. Anyway,
Yeah.
can we talk after?
Definitely. Would love to.
You and me too, or all three of us.
Thank you all.
Thank you.